It's my pleasure again to come to you and see how science does confirm biblical creation. One of the privileges I have as a scientist, I get to see aspects of God's creation that a lot of people don't get to experience, and it's just my joy to share that with others, and so that they can see God's majesty revealed in what He's created. There was a movie a few years ago, National Treasure, where Nicolas Cage finds a secret code on the back of the Declaration of Independence, and it leads him to other clues and so on. And obviously the code was put there by very intelligent people, and that implies intelligence when you find a code like that. What if there were a code embedded in numbers like 1, 2, 3, 4? What if there was a secret code embedded in them that we finally got around to discovering? What would that imply? What if there was a message inside numbers? What would that imply? It would tell us something about the intelligence of the person who made numbers. Now, we don't often think about God creating numbers because they're abstract. We think about God creating animals and stars and planets and so on. But numbers, God is responsible for them as well. Even though they're abstract and conceptual, God's sovereign over the abstract just as much as He is the physical universe. And as a matter of fact, there is a secret code built into numbers that was discovered in the 1980s. It's been there since creation, but it wasn't until the 1980s we got smart enough to finally decipher it. And it is mind-blowing. And this is something that I read about when I was pretty young, really, and it was mind-blowing to me. And I want to share this with you because I dare say there is no secular or atheistic explanation for what I'm going to share with you today. This secret code only makes sense in the Christian worldview. And so we're going to have to talk a little bit about that, what that means. When I was young, very young, and my mother would prepare these wonderful meals, but sometimes she would put broccoli on the plate, which I didn't really care for. And in rare moments of maturity, I would eat the broccoli first, get it out of the way, because the rule was you had to eat everything on your plate. So I'd get the broccoli out of the way first so that I could then enjoy the rest of the meal. You know what I'm talking about? Yeah. So in that spirit, we got some broccoli to do first. But stay with me because it's going to get really good. Okay? You won't be able to enjoy the rest of the meal unless you go through the broccoli. So we're going to talk first about sets. Now, a set in mathematics is just what you think it is. It's a group of, in this case, numbers that have a common defined property. And so you can have different types of sets out there. And in most sets, some numbers are included in the set and other numbers are excluded from the set. This is pretty easy, and it depends on how you define the set. So you could have the set of even numbers, those numbers that are evenly divisible by 2. And in that set, those numbers would be included in it, and those other numbers would be excluded from it. That's pretty easy. That's the set of even numbers. We could consider the set of negative numbers. Now that's a different set, isn't it? And so a different set of numbers will be included in there, and then those other ones will be excluded. Now for those two sets, you can tell just by looking at the number whether or not it belongs, right? In this case, if it doesn't have a little negative sign in front of it, it doesn't belong. And if it does belong. So that's pretty easy. You can tell just by looking at the number. But there are some sets that have a more complicated definition, and you can't tell just by looking at the number whether or not it belongs. And so we're going to talk about a particular set that's called the Mandelbrot set. This was discovered in the late 1970s, early 1980s, named after the person who really discovered this, Benoit Mandelbrot. He was a math guy and a computer guy. He worked at IBM. This set is defined according to this little formula that you see right here, where it's the set of all numbers, C. C is a number that is potentially part of the Mandelbrot set. We're testing it, for which this other number, Z, remains small according to this little formula. And it looks very complicated, but it's really not. I'll take you through it. The little n just means that that's a particular value of Z. N plus 1 is the next value of Z. So there's lots of values of Z. There's a sequence. And if that sequence of Z stays small, like if it's all zeros, that would be small, then the other number, C, is part of the Mandelbrot set. On the other hand, if the sequence of Z gets very big, if it goes 1 to 100, a million, a billion, then C is not part of the Mandelbrot set? And we'll do a couple of examples to let this sink in. It's pretty straightforward, really. So we're going to ask, is the number 1 part of the Mandelbrot set? So C equals 1, okay? And we're going to plug that into our formula then. So we have z squared plus 1, because that's the number we're testing. That becomes the new value of z. Now, the first value of z is 0 by definition. So that's the first value. So we plug that in, and we have 0 squared, which is 0, plus 1 is 1. Yeah, 0 squared plus 1 is 1, right? Even the Common Core folks got that one, right? Okay. So that's the next value of z, okay? And what we'll do is we'll put that 1 back into the formula. That's the new value of z. So now we have 1 squared, which is 1, plus 1 is 2, okay? And you plug that back in, so we have 2 squared is 4. 2 times 2 is 4, plus 1 is 5. Okay, you're getting this. You put it back in, 5 squared, 25, plus 1 is 26. Okay, we put that back in. 26 squared is a big number. And you put that back in. Okay, now you see what's happening here? Is the sequence of z staying small? No. So is the number 1 part of the Mandelbrot set? No. Because it has to stay small for it to belong. You see? So we'll do one more example just to make it clear. Is the number -1 part of the Mandelbrot set? So this time c equals -1, and we'll plug that in. So it's going to be z squared minus 1 is the new value of z. Z always starts as 0. So we have 0 squared, which is 0, minus 1 is -1. We put that back in. -1 squared is +1, right? Because a negative times a negative is a positive. Minus 1 is 0. We put that back in. 0 squared. Well, this looks familiar. 0 squared minus 1 is -1. Put that back. Oh, wait a minute. See what's happening there? 0, -1, 0, -1, 0, -1. Interesting. And you can see it'll do that forever. Is z staying small? Yeah. So is the number -1 part of the Mandelbrot set? Yes. Okay, you got it? Pretty easy, really. It's tedious, but it's easy, right? And you could check any number that way. All you could do is run it through that formula, and the sequence of z will either stay small, in which case the number is part of the Mandelbrot set, or the sequence of z will get big, in which case it's not part of the Mandelbrot set. And you could run that through, and it's easy as pie. It's just kind of tedious. There's one more complication, and then we get to the really cool stuff. The other complication is that the Mandelbrot set also includes what are called complex and imaginary numbers. Okay, so an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to understand, and so they call them imaginary. It's just a name. I hate that they have that name because it makes it sound like they don't exist. You know, they're fabricated. No, they do exist. Imaginary numbers do exist. And to add insult to injury, the numbers that are not imaginary they call real. But that's just terminology. Both are equally true, let's put it that way. But how do we have a number that times itself is negative? And it's represented by a lowercase I. That's the kind of the primary imaginary number when I times I is -1. How do we make sense of that? After all, imaginary numbers are not positive because a positive number squared is positive. And yet, the imaginary number times itself is negative. Imaginary numbers are not negative because a negative number squared is also positive. And imaginary numbers are not 0 because 0 squared is 0. Weird. So we have a number that's not positive, it's not negative, and it's not 0. And that leaves us kind of scratching our heads a little bit. We have trouble with that. Well, I got news for you. Not everything in this universe is intuitive. If you've ever had a class in quantum mechanics, you know, the universe doesn't work always the way that we expect it to. You know, our intuition really is based on experience. And the fact is most adults don't have experience with imaginary numbers, and so they seem strange. But it's just a matter of experience. When you were a little kid, negative numbers probably didn't make a lot of sense, right? You know, I can have 1 apple, I can have 2 apples. How can I have -2 apples? That doesn't make sense. How can you have less than nothing? You get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yes, I can have less than nothing. Well, imaginary numbers are the same way. You gain a little experience and you find, yes, there are numbers that when you square them, you get a negative. But they're not positive, they're not negative, and they're not 0. How do we make sense of that? One way to do it is if you consider a number line. So here we have a number line. Now, the positive numbers are to the right of 0 along that number line. The negative numbers are to the left of 0 along that number line. So how do we represent a number that's not positive, not negative, and not 0? Well, you put it up above the number line like that. It's not on the number line. It's on a different axis. And by multiplying I by the other real numbers, you can have all kinds of imaginary numbers. And you can think of them as being on a different axis. So the real numbers are along this axis, the imaginary numbers are along that axis. And that makes sense. You can see that the imaginary number, it's not positive because it's not to the right of 0. It's not negative because it's not to the left of 0, and yet it's not 0. That kind of makes sense. And then you can also have numbers that are called complex, and they're off axis. They're called complex because they have a real part and an imaginary part. But it's one number with two parts. And usually the real part is represented by the x-axis, and then the imaginary part is represented by the y-axis. And so you can plot any number in a plane by those two components, the real component being the x and the imaginary component being the y. That's kind of neat. I can represent any number on a plane. Very convenient. So the Mandelbrot set also includes these imaginary and complex numbers. And the only thing you need to remember, they obey all the ordinary rules of algebra. It's just that when you multiply I by itself, you get -1. That's the only thing you have to remember. Everything else, it's just ordinary algebra. So what we can do then is we can make a map, because I'm trying to figure out if there's a pattern to the numbers that belong to the Mandelbrot set. And it turns out there is. But it's not obvious, right? Because you can't tell just by looking at a number whether it's going to belong or not. You have to run it through that formula, and that's kind of tedious. But in the 1980s, computers were starting to get fast enough where they could iterate that formula a number of times, and they could analyze to see whether z is getting big or staying small. And so what we can do is we can have the computer check all these different points, and we'll see if there's a pattern to the Mandelbrot set. And so we'll take the points that belong to the Mandelbrot set, and we'll color those black. That's arbitrary. That's the way Benoit Mandelbrot did it, and we follow his example. So, and you have the computer check more points, and you find that all those points right there belong to the Mandelbrot set. When you run it through that formula, z stays small. And then the points that do not belong, we'll color those red, or some other color. It doesn't really matter. And so we already checked the point 1. We found that the number 1 does not belong to the Mandelbrot set, so it gets colored red. And had we checked these other points, we would find that they do not belong. And so you see, as you plot more and more of these points, a pattern starts to emerge. What's it going to look like? Well, you have the computer run through thousands and thousands of points. You have the computer check each one of those numbers, and a pattern emerges, and the pattern looks like this. It's really interesting and unexpected. Nobody was expecting that when you made a map of the Mandelbrot set, it would look like that. Remarkable. And so let me remind you again what you have here. It's a plot of the points that do or do not belong to the Mandelbrot set. The points that are colored black do belong. The points that are colored red do not. And I even shaded it, so points that are almost on the Mandelbrot set but not quite are bright yellow. And so it's kind of shaded. So if the sequence of z goes to infinity really quick, it's dark red, and if it goes to infinity slowly, it's kind of a bright yellow. So it kind of, you don't have to do it that way, but it increases the contrast, makes it easier to see. So now we don't have to run it through that formula because the computer's already done the hard work for us. We can look and we can see that the number -1, you can see it's part of the Mandelbrot set. You can see that the number 0 is, had we run it through the formula, z would stay bound and so on. The half I is part of the Mandelbrot set. So I'm going to remove the axes now, because it turns out the shape is remarkably interesting and unexpected, and it'll turn out to have a lot of beauty in it as well. The shape itself is, I mean, this is a mathematical plot. I guess we'd expect it would have some mathematical properties to it, but everyone was surprised by the properties it has. The main shape that looks kind of like a heart, that's called a cardioid. And a cardioid is what happens when you take a circle and you take your pencil on it and roll it around another circle of equal size. The shape you'll get is a cardioid. And you can see that, sure enough, the main part of the Mandelbrot set is a perfect cardioid. All the other shapes that are growing off of it are circles. All these perfect circles attached to the perimeter of the Mandelbrot set. And then you see some other features, like these little tendrils that grow off of it, and a spike over on the left, kind of that juts out. That's kind of interesting. What's that all about? Well, The interesting thing is we can zoom in on this because we can have the computer plot it at higher resolution, and we find that this shape has some really interesting mathematical properties to it. You notice that that top circle there, it's got a circle on top of it, another one on top of it on smaller and smaller scales, and it goes out and forms this little tree, and it's got 3 stems to it, including the trunk. So it's got a trunk and 2 stems for a total of 3 branches. You see that there? Now the next one to the left branches into 5. Can you see that? I mean, it's kind of small, but you can see the 5 branches there. The next one is 7, 9, 11, 13, 15. It's all the odd numbers. And by the way, they don't stop. They go to infinity. There's an infinite number of them. They get smaller and smaller, though, and so you have to zoom in more. So somehow the Mandelbrot set knows how to count. It's kind of remarkable. And then on the other side, you have the odds and the evens. You have all the numbers there in terms of the number of branches. Now, it's remarkable enough that they have branches at all, because who would have thought that when you run numbers through that little formula, you get that shape? It's remarkable. Nobody was expecting that. And it's even more remarkable that it has the ability, apparently, to count in terms of the number of tendrils that grow off of each bud there. And, of course, you can take 2 of those numbers, like 5 and 3. Now, 5 plus 3 is 8, okay? And it turns out that the bud in between those 2 has 8 tendrils. Interesting. And that's true of all of them, both on the left side and the right. The bud in between the 2 adds the number of tendrils on each one. So not only does the Mandelbrot set know how to count, it knows how to add. Interesting. And strange and remarkable. Well, let's go back out take a look at the overall shape here. So again, you have that cardioid, that's the heart-shaped structure, circles growing off of it. And then on the left side over there, you got this kind of spike that goes out. And you see there's this little bump on the end of the spike. So let's take a look and see what that looks like. So we'll zoom in on it. And that little bump, turns out, it looks like the entire Mandelbrot set. It's a mini Mandelbrot set. And it's almost identical to the parent, except it's got extra spikes growing off of it. But the basic shape's the same. It's got the cardioid and the circles. And, it has a little spike growing off of it, too, with a little bump. What could that be? Well, let's zoom in on that. And, interesting. Absolutely fat. And it's got extra spikes growing off of it. And that's got a little bud. How about that? Now, of course, you could do that literally forever. And there's an infinite number of baby versions built into the Mandelbrot set on smaller and smaller scales. Fascinating. Absolutely fascinating. And take a look at how small this is compared to the original when we zoom back out here. Look at how tiny it is. Isn't that remarkable? And the fact that it repeats infinitely, and it doesn't lose complexity, it actually gains it each time you get more extra spikes growing off of it. Very remarkable. Well, to anticipate my conclusion in this, I'm going to suggest to you that this shape tells us something about the way God thinks. God's understanding is infinite. Numbers are an aspect of God's mind. God is responsible for numbers. And so it makes sense in the Christian worldview that when we explore and study numbers, we find intelligence in them. We find evidence of patterns. And not only intelligence, but infinite intelligence, because this thing repeats infinitely. A structure that repeats itself on smaller and smaller scales is called a fractal. So the Mandelbrot set is one example of a fractal. There are other types of fractals. There are other sections of the Mandelbrot set that are fractal. We could zoom in, for example, on one of these little tendril features here and zoom in on that. And you'd say, well, that's interesting. You think what's going to stop at some point, right? Eventually it'll even out and but it just keeps going. It's infinitely wiggly, you see. It's wiggling around like that, and you zoom in on it, and it keeps going and keeps going and keeps going. It's just mesmerizing to watch this thing and see the scale here. And it gives you a little taste of what God's mind is like, to be able to think infinitely. We can only process just a little bit of information at a time, but God's mind is truly infinite. So one of the interesting areas to explore, and what I want to do now is just kind of spend some time exploring this shape that exists in the mind of God and has existed in the mind of God from creation, that was only discovered in the 1980s. And we can zoom in, for example, on this cusp between the main cardioid and the disc. And we find they call it the Valley of the Seahorses, because you see over on the right side, it looks like seahorses. They're upside down, because the way we've zoomed in on them here. Now, the colors are arbitrary. I can make them whatever I want, and we'll change them every now and then just to keep things interesting. But just keep in mind, black always represents numbers that do belong to the Mandelbrot set, and then colors represent those that do not belong to the Mandelbrot set. And bright colors are very close to being on the Mandelbrot set, but not quite a part of it. So let's zoom in on one of these seahorse structures over here. You see it looks like an upside-down seahorse. Isn't that fascinating? And quite beautiful. And I need to explain a little bit about what this means, because if the points are very bright, that means it's very close to the Mandelbrot set. And you might look and say, but yeah, that bright hub doesn't look like it's anywhere close to it. It is. It's just, you need to realize that there is a very thin black thread that's wiggling around and making that shape, you see. It's just so thin, it's thinner than the pixels that the computer can plot. So everywhere you see structure like that, there is a very thin black thread that's winding around and creating that wonderful shape. So really quite remarkable. And who would have expected that little formula, z squared plus c, when you run numbers through it and you find out which ones belong, you get that. I think it's amazing. Well, let's zoom in and find out what this seahorse is made of. It's the central hub there looks kind of like a spiderweb type structure, right? You got the spokes and the rims around there. And I've found from experience you can zoom in on the center of that till your heart's content, and it doesn't really change very much. It goes on infinitely. So again, the infiniteness of the mind of God. And so I thought, well, okay, let's go off to the side and figure out what the strands of the spiderweb are made of. So let's go off to the side here, and we find that the strands are made of more spiderwebs, which is kind of interesting. And we zoom in a little bit more, and you find that there's sort of two hubs there. You see the bright yellow hubs. And then in the middle, it goes from 2 to 4. And as we zoom in, it'll go from 4 to 8 to 16, 32, 64. It doubles each time. And as we zoom in on that central hub, we find, oh, isn't that interesting? You see it going from 4 to 8 to 16 and so on, and in the middle, of course, you have another baby Mandelbrot set. Quite fascinating, really. And again, there's an infinite number of these babies built into the overall shape, which I think is amazing. And again, look at how small this is compared to the overall shape as we zoom back out. It's just a tiny little infinitesimal, and we could have zoomed in on any one of those strands. I just picked one at random, and there it is. So pretty remarkable. Let's go back to that valley. Now, the valley of seahorses is on the right. On the left, we find the valley of the double spirals. And I'll zoom in on one of those now. This is my favorite part of the Mandelbrot set. I think they're very beautiful. They remind me of spiral galaxies, actually, which is an astronomer I really appreciate. God apparently likes spirals because he's built a lot of them into nature, and he's built them into math, which is remarkable. Who would have guessed that there would be a spiral, a beautiful spiral, built into that little formula, z squared plus c, or rather built into numbers when we run them through that formula. Pretty amazing. It's a double spiral because there's actually two strands that wrap around each other. If you trace one strand, you'll find that there's a strand in between. And so it is a double spiral, as are spiral galaxies, by the way. And let's zoom in on that a little bit. And again, I've found you can zoom in on the center forever, so we'll zoom in on the side. And you find the spiderweb type structures, you find more double spirals, and you find a new structure. I call them bow ties. They're kind of in the middle. You see it looks like kind of like a little bow tie, right? And it's got two double spirals that intersect in the middle. Quite beautiful. Again, what you're seeing here, the Mandelbrot set, it's just incredibly wiggly. It's so wiggly. It's making these wonderful shapes. And that's what the points that are very bright are very close to that thin black thread that's wiggling around and making all these wonderful shapes. So we'll zoom in on one of these bow ties, and we find that again, you have the two double spirals. We zoomed in on a double spiral, and we found that it's made up of multiple double spirals. And they go from 2 to 4 to 8 to 16 as we zoom in on the center there. And in the middle, you find another mini Mandelbrot set. You're not surprised this time, but there it is. And quite beautiful. Who would have imagined that such beauty would be built into numbers? Well, in the Christian worldview, that makes sense. We serve a God who is beautiful, who makes beautiful things. And when we examine the way God thinks about numbers, which is what mathematics really is, we find it's immensely beautiful. Who would have thought? The Christians would have thought. So the other valley we can zoom in on that's kind of interesting, they call it the Valley of the Elephants, and that's the main cusp on the main cardioid there. Mathematicians like to give fun names to these things, but you can see it kind of does look like elephants marching one after the other. You see the elephants there, especially on the bottom. Now on the top, they're hanging from the ceiling, but if we zoom in on a couple of these elephants, you can see that elephants marching after each other with the trunk all curled up. Isn't that interesting? And you see each one of those circles has an elephant growing on top of it, and there's an infinite number of those circles. They get smaller and smaller and smaller, and the elephant's trunks get more and more twisted as you go further in, which is kind of interesting. So what happens when we zoom in on one of these elephants? Well, let's zoom in on the trunk, because that's a spiral, and I like spirals. Now this is a single spiral, so it's one strand wrapped around itself. And as you zoom in on that, there we go. So we'll zoom in on these strands. And again, you find the spiderweb type structures. You find single spirals now, because we zoomed in on a single spiral. And as you go in even further, you find bow ties, but the bow ties are made up of single spirals this time. And what happens when we zoom in on the center of that bow tie? What do you think we're going to get? Let's keep going here. There we go. Lo and behold, right in the middle, another baby version. Let's get even closer there. Look at that. Isn't that stunning? And notice that the stuff that's growing around the perimeter of this little baby version, you got spirals and all these other stuff, because the baby version inherits the characteristics of the section of the parent that it grows off of. So we zoomed in on a spiral, and we get lots of spirals around the exterior of the baby. And notice that on the by the way, it's flipped around too. And it's because we've zoomed in on a spiral, so it's been rotated. But you notice it has a little spike there on its right side, and there's a little bump on that. What do you think that is? Of course, it's another baby version. But the more you zoom in, the more computing power it takes. And so the computer gets slower and slower, and at some point you say, I give up. So anyway, all that, just a map of what numbers belong to that little formula when you run them through that algorithm. Isn't that fascinating? And this, of course, was astonishing to mathematicians when this was discovered back in the 80s. So then it occurred to me, well, is there something special about that formula? I mean, did we just happen to stumble upon to an amazing formula? What happens if we change it? So I thought, okay, let's take, what happens if we go z cubed plus c? Well, I ran the computer code through that, and it turns out you get a different shape. Interesting. And very similar in some respects, but different in others. The shape here, the main shape, is called a nephroid. A nephroid is what happens when you take a circle half the size of another and you roll it around, then you get that shape. And you can see it's a perfect nephroid. Really amazing. And then instead of circles growing off of it, you have cardioids growing off of it. Notice everything's gone up by one. The Mandelbrot set had a cardioid which has one valley. This one has a nephroid which has two. And the circles growing on it, which have no valleys, now are cardioids which have one valley. Everything's gone up by one. That kind of makes sense. We went from z squared to z cubed. I guess that makes sense. You can also plot the intermediate powers if you want to. You know, what z to the 2.1, z to the 2.2, and so on. And when you do that, you can see how the shape gradually changes from one end to the other, which is kind of interesting. And so you can kind of see, you can kind of compare the two shapes. Now, the one aspect that has not changed very much is the Valley of the Elephants. You notice that on the right. It really doesn't change very much between the two. And let me fire up this other part 2 here. So I thought, what happens if we zoom in on Elephant Valley? Is it going to look the same? Will we have elephants again? Let's find out. It's fun to explore these shapes that are built into numbers. Lo and behold, we have elephants. It's kind of interesting. See the elephants there marching one after the other? Now, interestingly, before, remember, we had circles, and we had one elephant growing off each circle, and there were an infinite number of circles, and therefore an infinite number of elephants. Now we have 2 elephants growing off of each cardioid. So the elephants have multiplied. Each one has become 2. We had an infinite number of elephants, and now we have twice that many. That's kind of mind-blowing, isn't it? Infinity is a weird concept, but it's a true concept because it's true to the mind of God. When we zoom in on this, what do we get? Zoom in on the trunk there. Again, you find these wonderful spiral structures. It's a single spiral, as it was in the Valley of the Elephants on the Mandelbrot set. Zoom in a little bit more. You find some interesting structures there. Will we find bow ties? Well, we had bow ties before where they had 2. Now we have 3. You see, it's gained an extra loop, which kind of makes sense. Went from z squared to z cubed, and you get 3 of them now. And in the middle of that thing is, lo and behold, another one of these shapes. So it's a fractal as well. It repeats itself infinitely on smaller and smaller scales. They often call this a multibrot because it's a multiple of the Mandelbrot. And there's other multibrots. You could say, okay, what happens when we go z to the 4th? Well, that's what you get. Okay, what happens if you go z to the 5th? Interesting. You notice the number of lobes is 1 less than the number. So z to the 5th, you get 4 lobes. Z to the 6th, you get 5 lobes. It occurred to me if I went z to the 7th, I could get snowflakes. And you sure do. And if you zoom in on it, do you get snowflakes? Absolutely. You zoom in on it, you get snowflakes everywhere. Isn't that wonderful? Did you know that such beauty was built into numbers? No one did before 1980. No one other than God. I tried playing with negative powers. You get fractals with negative power. Z to the negative 2, so that's the 1 over z squared. You get these kind of interesting shapes. You get kind of a pebble-like structure. It's stunningly beautiful. At least I think it is. We zoom in on that. Is it fractal though? Does it repeat itself on smaller and smaller scales? Well, let's check it out. Let's zoom in a little bit. Sure does. It goes on infinitely, doesn't it? And you can see how that pebble structure continues on and on and on. Stunningly beautiful. Stunningly beautiful. And all built into numbers by the creator of numbers. Just a little window into the mind of God. So that's z to the negative 2, z to the negative 3 will get you that, z to the negative 4, z to the negative 5 is another way to make snowflakes. They're inside out now. Okay, remember the black points belong to the shape, so most of the universe belongs, and then the inside doesn't. So it kind of flips it inside out when you take a negative power. Okay, so what does all this mean? We got these wonderful shapes, and it's very pretty, Dr. Lisle, but who cares? Well, I want to ask, what causes the beauty in fractals? Because I think you'd agree they're beautiful. They're beautiful, and they're certainly complex, and so I have to ask what causes the complexity in them. The fact that when you zoom in, you get not only baby versions, but the complexity increases as you zoom in rather than decreases. What's causing that? So let's answer the first one first. What causes the beauty in fractals? And I'll have several possibilities. Could it be the man-made color scheme? Now, I told you that the colors are arbitrary, other than we always assign black to the set itself. And then we assign other colors to the perimeter to make it easier to see. And I'll admit, I picked the colors. I think they're pretty. Other people pick other colors, sometimes not always pleasant ones, and shame on them, because, you know, I do have an artistic side. I appreciate beauty anyway. Is it the man-made color scheme? I would say no, because although I think the color enhances the beauty of these, even in grayscale, they're still beautiful. There's something about that shape that is attractive to us. We see beauty there. The shape itself is beautiful. I think the color enhances it a little bit, the way putting a little bit of salt on your food brings out the flavor a little better, but it certainly doesn't create the beauty. I picked the colors, but the shapes are God's. Did the computer create the beauty? Now you might have said, well, the computer plotted that. But remember, we did the first 2 points manually, right? We checked it and ran it through that little form. You could plot this thing manually if you wanted to. It would be horribly tedious, but you could do it. And it was, that's why it wasn't until computers that people started plotting this thing. But it's not the computer that created the beauty. The computer just revealed it quickly. It did something that would take us a long time to do. It did it fast. But you could do this thing manually. Did people make this? Did Benoit Mandelbrot create the Mandelbrot set? He defined that formula, but did he create the beauty and the complexity? Well, of course not. He was surprised, as was everyone else. And some people didn't believe it when this was first discovered. They thought maybe it was some kind of artifact, some problem in terms of the way the computer is coding. But it's not. That's now been disproved. These things are real. The computer just allows us to view them quickly. People didn't make it. People were surprised by this result. And obviously you wouldn't be surprised by something you yourself made, right? You create some kind of design, you say, well, how about that? I had no idea it would be like that. No, this was, and frankly, we can't make things that are infinitely complex anyway, right? Because we don't have the time, for one. I would say the beauty is built into math. It is. It's always been there. It wasn't until the 1980s that we had the ability to view it. What causes the complexity in fractals? These intricate shapes that can add and they can count and so on. What causes all that complexity? And the fact that it's infinitely complex. You have an infinite number of baby versions built in to the original. What's causing that? Was it the computer? Well, again, the computer is simply revealing the complexity. It was already there. The computer didn't create these shapes any more than a microscope creates bacteria. A microscope allows us to view bacteria. The computer allows us to view these shapes, and it does so very quickly. It didn't create it. Did human beings create it? Well, again, we can't create things that are infinitely complex, right? We don't have the time. We don't have the capacity to do so. It's not like somebody sat down and said, I'm going to draw a cardioid here, and then I'm going to draw a circle. No, that's just what you get when you see which numbers belong to that little formula. Did the formula create it? Well, in a sense, we had to run the numbers through that formula to reveal that shape. But the fact is, when we changed the formula, what happened? We still got beauty, right? So it doesn't matter too much what formula. Not all formulas will reveal fractals, but my point is, a lot of them will. And we could explore those. And so, in a sense, it's not the formula is not that important. Because you can change the formula, you still get beauty, you still get complexity. In a sense, the complexity is built into math itself. So how do we make sense of that? How do we make sense of beauty and complexity being built into math? What is math? Well, math is the study of the relationship between numbers, right? The rules governing how numbers relate to each other. That's pretty easy. And then of course I'm going to ask, what are numbers? Well, come on, Lisle, we know what numbers are. It's funny, some of these things that are very basic are hard to define, aren't they? Like consciousness, it's hard to define it without using another word that's basically a synonym of consciousness. What are numbers? The best I've been able to find, and different dictionaries disagree, but the best definition I've been able to find is that numbers are a concept of quantity. And I think that's a pretty good definition. That's the best I've seen. Numbers are a concept of quantity. So if you have 3 apples, the apples are not the number. The apples are physical, right? But the 3-ness is a concept. It exists in your mind, and it's separate from the apples. It's a concept. So numbers are concepts. Concepts exist in a mind. Numbers are abstract in nature. They're not physical. They exist in the mind. You can't physically touch a number. You can't literally see a number, by the way. You might say, well, wait a minute, I see the number 3 there. Is that really the number 3? If it is, then I just destroyed the number 3. And poor students will now have to count 1, 2, 4, and so on, because you said that was 3 and I removed it, so there's no more 3. Well, obviously that's not the number 3, that's a representation of the number 3, right? It's a written numeral. Numerals are not numbers, they're representation of numbers. And at some point in history, we decided that shape would represent 3 things. And of course, you can use Roman numerals if you like, and they have a different notation. They represent the same concept, though, don't they? So the concept, that's not something we created. Laws of mathematics are conceptual, not physical. You can't stub your toe on a law of mathematics. You can't stub your toe on a number. You can stub your toe on something that's physical, but not on numbers, because they're conceptual. So where do laws of math come from? And of course, this is the question that gets back to origins, right? Because the secularists try to explain everything naturally, and especially by evolutionary processes. But did laws of math evolve? That's something to think about. I mean, we find lots of patterns in nature. We find, different patterns in animals and the way animals are classified. And the way secularists explain that is evolution. They say, well, they had a common ancestor and then they evolved, they changed. Will that work for math? Did 7 used to be 3, but it evolved? That doesn't make any sense, does it? Numbers are what they are, and they've always been what they are. Laws of math didn't evolve. It's not like, the Pythagorean theorem wasn't true, but then eventually, triangles came. No, they don't evolve. Laws of math have always been the way they are. Were laws of math created by people? Some people argue that, but that's a ridiculous assertion. Because if we created them, we could have created them different. We could have said, you know what, let's all agree that 2 + 2 = 5. Now, you could imagine an architect trying to live out that philosophy. It's not going to work out well for him. Or try that at your bank. It's not going to work, because it's not true to reality. We did not create laws of math. We discovered them. Pythagoras, right? He wasn't the first to discover, but the Pythagorean theorem, right? Now, did triangles not add up that way before Pythagoras? Well, of course they did. He just discovered it. The planets, the way the planets orbit, they obey mathematical laws. Kepler's laws, p squared equals a cubed in terms of the relationship. Was that not true before people came along? Planets orbited perfectly well for the 2 days before people. Do laws of math come from the universe? Some people have argued that. They say, well, math just describes the way the universe is. Now, that's interesting that the universe does obey mathematical principles. But math can't come from the universe for a number of reasons. First of all, the universe is constantly changing. It's expanding, and stars explode every now and then, and so on and so forth. Animals live and die, and so on. If math was contingent upon a changing universe, you'd expect math would be changing, wouldn't you? And so numbers might be evolving, but that's not true to reality. Not at all. And frankly, some math goes beyond the universe. The universe has 3 dimensions of space, 1 of time. In mathematics, you can have as many dimensions as you want. And you can talk about the hypervolume of a hypersphere, a sphere that's in 4 dimensions, the 4-dimensional equivalent of a sphere. And that's meaningful. And yet it has no application in the physical universe. Math goes beyond the physical universe. You can do stuff with infinities in mathematics. All calculus is based on that. Stuff in the real universe, apparently the number of atoms is finite, at least in the visible universe. So it didn't come from the universe. I would suggest to you that laws of math stem from the mind of God. Laws of mathematics are the way God thinks about numbers. And that makes sense of the laws of math and their properties, because laws of math are conceptual. They exist in a mind. They are universal, meaning they apply everywhere. They're invariant, meaning they don't change with time. And they're exceptionless. It's not like 2 + 2 = 4 most of the time, but every now and then it equals 7. They're exceptionless, right? And if you think about it, all those characteristics make sense in the Christian worldview, where mathematics is a reflection of the way God thinks about numbers. Laws of mathematics would have to be conceptual because God's thoughts are conceptual. That makes sense. Laws of mathematics are universal. They apply everywhere because God is omnipresent. Right? Laws of mathematics are invariant because God doesn't change with time. God's beyond time and made time. Laws of mathematics are exceptionless because God is sovereign. There's no aspect of creation that is out of his control. But if you think about it, none of those properties of laws of mathematics would make sense in a secular or naturalistic worldview. Or how could you even know? I mean, somebody might suppose, well, I think laws of math are universal, but how could you possibly know that? Everybody assumes it. I guarantee you, all astronomers, at least all the ones I've ever met in my career, all believe that mathematics works the same way in the Andromeda Galaxy as it works here on Earth. And you couldn't know anything about Andromeda Galaxy if you didn't assume that. You assume the laws of physics are the same there. You assume the laws of mathematics are the same there. How do they know that? Have they been there? Of course not. It's in the Christian worldview that we would say, hey, God's sovereign over the entire universe. He's omnipresent. Of course they're going to work the same way there as they work here. All mathematicians assume that laws of mathematics are the same tomorrow as they were yesterday. That makes sense in the Christian worldview, and yet it makes no sense in a secular worldview why there should even be laws of mathematics, let alone why they do not change with time. Or how could you possibly know that? How can you know anything about a future you've never experienced from a secular worldview? They'll try and turn it back. Well, how do you know the future? Because I know God, and God is beyond time. And he's told me some things about the future. So you see, all of the characteristics of laws of mathematics make sense in light of the fact that mathematics stems from the mind of God. The naturalist has a dilemma, however, because laws of mathematics are conceptual. They exist in a mind. We know that. Something's a concept that exists in the mind. And so 2 + 2 = 4, that's a concept. And there are other mathematical truths you could think of. They exist in the mind. But they also existed before people, right? Because again, the planets orbited before people and they obeyed mathematical laws. It's not like the planets were just chaotic before human beings, right? Came around and created math. So that you see, the naturalist has a dilemma, because on the one hand, he knows that mathematics requires a mind, but on the other hand, he knows that mathematics exists before human minds. But the naturalist doesn't have minds before human minds, you see. I mean, animals they can't really do math. So he's got a problem. But the Christian can make sense of this because we have a mind before human minds, and that is the mind of God. And the mind of God not only makes sense of laws of mathematics, but their properties as well. Their universal, invariant nature. Now, fractals, perfect fractals, the kind we've looked at so far, repeat infinitely. You can zoom in on the Mandelbrot set forever, and you will continually find smaller and smaller versions, baby versions of it. You can do that forever, or until your computer blows up. So perfect fractals repeat infinitely and are only found in the conceptual world of mathematics. Nonetheless, the physical world contains approximate fractals, things that they go so many steps and then eventually they break down into atoms, and atoms are not fractal. But let me give you some examples of these. Snowflakes. Snowflakes have a fractal quality to them. They have that six-fold symmetry. You zoom in, you still get six-fold symmetry. You zoom in, you get six-fold symmetry. These little gems that God sends us from heaven every year, and we brush them off the car, and yeah, they're beautiful, and they're fractal. They don't repeat exactly, but nonetheless, the six-fold symmetry continues no matter how much you zoom in. And so it's hard to tell the size of a snowflake unless you have something to compare it to, because no matter how big it is, it always looks kind of the same. That's a characteristic of fractals. That stuff that grows on your windows in the winter. I was fascinated by this when I was a kid. Really, I still am. I think it's beautiful. How it grows on your windows. Fractal shapes, quite lovely in terms of the way they repeat. They branch and they branch into branches and so on. Ferns are fractal because you see ferns have a stem, and they have another stem growing off of that, and another stem growing off of that, and then the little leaflets and so on. They branch and branch into branches and branch into branches of branches. I even found fractal broccoli, so I guess broccoli is good for something after all. There you go. Romanesco broccoli, they call that. And you can see it's kind of a cone-shaped, and then it's got cones growing on it and cones growing on the cones on smaller and smaller scales. It's fractal. Isn't that fascinating? Too bad it tastes horrible. Coastlines are often fractal. Coastlines, the way they branch, you zoom in on them, they branch into branches and so on. Mountaintops are fractal. You look at them from above, and they kind of branch, and they branch into branches and so on. Clouds tend to be fractal. They don't repeat exactly, but am I looking at the entire sky, or am I looking at one very small section of a cloud? It's hard to tell, because the same kinds of patterns repeat. The way lightning branches is fractal, because you have a main bolt that branches into smaller bolts, which branch into smaller ones, and so on. And so lightning, very beautiful, and because it has that fractal quality to it. And it's really neat, too, when you watch it in super slow motion. You can see how it branches out into all these different branches. That's a fractal, till the leader connects, and then most of the current goes down the leader. Quite fascinating. So here's my question, then. Why do fractals occur both in math, which exists in the mind, it's conceptual, and in the physical world, which is made up of atoms and does not exist in your mind? Right? I mean, you have this shape, that's a multibrot, that exists only in the conceptual world of mathematics. We can plot it, but you could never touch that thing because it's not physical. It's not made up of atoms. But that one is, and they look remarkably similar. This particular shape here is part of the Mandelbrot set. Looks like a bolt of lightning, but it's not made of atoms. This one is. How is it that conceptual things that exist only in the mind also occur in the physical universe? This particular shape, that might look like a plant. That's actually a mathematical graph called a Barnsley fern. And a Barnsley fern is such that each leaflet is the entire shape. Let me show you. Isn't that interesting? Let's do it again just because it's cool. See, the entire shape, each leaflet is the entire shape. Fascinating. You can't touch that, though. It doesn't exist in the physical world, but that does. It's very similar. This stuff right here, that's a mathematical graph. That doesn't exist in the physical world, but that grows on your windows. This particular mathematical shape, cones on cones, it does not exist in the physical world, whereas this, unfortunately, does. This particular shape, that's part of the Mandelbrot set. It's a double spiral. You can't see that in a telescope because it's not made of atoms. It doesn't exist physically in the universe, but that one you can see it in a small telescope. The Whirlpool Galaxy, not too far off from the Big Dipper. So how is it that math, which is conceptual, you find these shapes, and then in nature, which is physical, you find the same kinds of shapes? Why is that? Now, one answer to this And a skeptic might say this. He says, well, the physical universe obeys mathematical laws. So it stands to reason if something can occur in math, it can occur in the physical world because the physical world obeys math. Okay, I'll grant that. But then I'm going to have to ask, why does the physical universe obey mathematical laws? And that is a stumper, if you're not a Christian. If you're not a Christian. In the Christian worldview, I can make sense of why the physical universe obeys math. Because the universe, the physical universe, is upheld by the mind of God, and God thinks mathematically. So it stands to reason the physical universe will obey mathematical laws, because God upholds all things by the word of his power, the Bible says, and in him all things consist or hold together. God thinks mathematically, and therefore the way he upholds the universe will be mathematical. It's inevitable. But I submit the secular worldview cannot answer that. They can't explain the properties of laws of mathematics, why they are conceptual, universal, abstract, invariant, exceptionless, and why the physical universe is compelled to obey them. Why would a physical universe obey conceptual laws? You come up with something in your mind, does the universe automatically just obey it? Of course not. It doesn't make sense. And unless you think I'm making this up, some brilliant people have written on this topic. Dr. Eugene Wigner, who is a PhD physicist, I believe he's a Nobel Prize winner, brilliant man. He wrote a wonderful article years ago, I love this article, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Interesting. Now, he's coming at it from a secular perspective. And from a secular perspective, he's perplexed. It's unreasonable that mathematics should work so wonderfully in explaining the physical universe, mathematics being abstract, the physical universe being physical. And so he discusses this in the paper. This perplexing dilemma is, why does the universe obey math? He says it's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to define them. He's saying it's amazing, first of all, that the universe obeys mathematical laws. That in itself is astonishing. And what's even more astonishing is that human beings can discover those laws. That's remarkable. Almost like a miracle. Yeah. What is his conclusion? Does he come up with an answer? From a secular perspective, here is his conclusion. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. Isn't that interesting? There is no answer from the bankrupt evolutionary atheistic camp as to why the physical universe obeys mathematical laws. But it is exactly what the Christian would expect. It's exactly what we'd expect. So we've seen that there's beauty of infinite complexity built into numbers. Numbers are abstract conceptions of quantity. They exist in the mind. Concepts require a mind, and numbers are a reflection, therefore, of the way God thinks. It makes sense in the Christian worldview. The secular worldview cannot cogently account for the existence and properties of numbers and mathematical relationships, mathematical truths. It can't make sense of it. It doesn't make sense in their worldview. Numbers existed before people, yet they are conceptions, meaning they require a mind, and that means minds existed before people did. And that makes sense in the Christian worldview. We can have that. It makes sense. Laws of mathematics are universal, invariant, abstract entities. It's exactly what we'd expect, given that God is omnipresent. He doesn't change with time. And, of course, all thinking is abstract. The physical world has approximate fractals, and we'd expect that, but the secular worldview can't answer it. The secular worldview cannot account why the physical universe obeys mathematical laws. It really can't. And we saw some of the brightest people in the world have worked on that, and they've not found a cogent answer. But it makes sense in the Christian worldview because the physical universe, like the world of mathematics, is controlled by the mind of God. And the reason we're able to do science is because God has graciously given us access to some of his thoughts. That's revelation. That's what God is. God imparting information to human beings. He's done that most specifically in his word, but he does it in our, he writes his moral law in our hearts and so on. We can make sense of math and this secret code of creation that's built into it. We can make sense of these wonderful shapes being built into numbers by the mind of God. And why they're beautiful. Because God, that's the nature of God. That's what it comes down to. God bless.